Here are your objectives for 3.2. Number 1, identify polynomial functions. Number 2, recognize characteristics of graphs of polynomial functions. Number 3, determine end behavior. Number 4, use factoring to find zeros of polynomial functions. Number 5, identify zeros and their multiplicities. Number 6, use the intermediate value theorem. Number 7, understand the relationship between degree and turning points. And number 8, graph polynomial functions. You ready? So first of all, you got to be able to identify whether a function is a polynomial or not. Okay? So let me just give you this to start with. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a squared x squared plus a sub 1 x. I think I said a squared, I didn't mean that. Plus a sub 0. Okay? This highest exponent right here, now it's just, we represent it in the general form with n. It's just a number, right? It's the highest exponent. That's called a degree. And you're going to need to know that, okay? Especially when we're talking about recognizing characteristics of a polynomial, okay? So for something to be a polynomial, considered a polynomial, it's got to be in this form, okay? This right here, this term, is my leading coefficient, okay? When the exponents are in decreasing order, the very first one is called the leading coefficient. Got it? So I'm going to give you some expressions or equations, excuse me. And I want you to be able to tell me if they are polynomials or not. So first of all, is this a polynomial? Does it have decreasing order of exponents? Is that all that makes it a polynomial? No, but this one is a polynomial, isn't it? Okay, what is its degree? Yeah. Highest exponent, right? What's its leading coefficient? -3. Is it okay if I put LC for leading coefficient? You don't know what that means? Okay. Any questions about that one? What about this one? Is that polynomial? No, why not? So first of all, it doesn't have decreasing exponents, but the other thing you can't have is a fractional exponent. Okay? Fractional exponent is not a polynomial. Okay? So we don't care about either of these other two things, because we only care about these two things if it's a polynomial. Does that make sense? Okay? So what about this? What do you think? Is it a polynomial? Yeah, it is, right? Okay. If it's a polynomial, what do we want to ask ourselves? What's the degree? What's the highest exponent? 6. And what's the leading coefficient? -3. Why not? because of the negative exponent. So we don't have fractional exponents and we don't have negative exponents, do we? Okay. Any questions about that? So there's another way you can try to classify or identify polynomial functions, and that's by the graph. Okay? So if we look at this graph right here, is this a polynomial? Well, yes it is. And it is because it's smooth and continuous. What do I mean by smooth? No hard angles, right? It doesn't come to a point and then change direction, right? And what do I mean by continuous? It doesn't stop. There's not any breaks in it, right? So what about this one? Is that smooth? Yes, but it is not continuous, is it? What about that? Yes, because it's smooth and it's continuous. What do you think? No, why? It's not smooth. Not smooth. Because of that point right there and that point right there. So do you see what I mean by smooth versus not smooth? Yeah? How do you feel about identifying polynomial functions? And how do you feel about recognizing the characteristics of the graph of polynomial functions? Good with that? So let's talk about determining end behavior. Okay? Now, I'm mostly, here, at least here at the beginning, I'm going to talk about two graphs. Okay? We're going to take most of our notes based on these two graphs. And I'm choosing these two because these two are two that you were familiar with. We talked about them quite a bit in Algebra 2. We've already talked about them in this class as well, right? This is y equals x squared, a parabola. I kind of messed up right there. Please forgive me. It should be a little roundisher. And this one is what? Do you remember? Y equals x cubed. Yeah? Talk to me about the end behavior of this one on the left. What's happening all the way on the end of the graph? Where's it going? It's going to infinity up, right? So it's rising. What's happening on the right? It's also rising, isn't it? What about this one? What's happening on the left? It's decreasing or falling, right? And what's happening on the right? It's rising. Now, why would I choose these two as the examples for this? This one, they're doing the same thing, and this one they are doing opposite. Does that make sense? So, just to remind you, what's the degree again? Highest exponent And what are we calling LC? What are we calling that? Leading coefficient. So just as a reminder, because it was on the other page, but it's not on this one, I'm just going to write it down for you again. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a to the 0. I'm telling you right now, a to the n does not equal 0. This first term does not equal 0. Okay? What you need to be able to tell me is the end behavior. That's what we're talking about right here. So what happens if n is even? Well, think about this one right up here. Is this n, this degree, is that even? Yeah? So referring to this graph right here, when n is even, what's true about the end behaviors? They are the same. If the leading coefficient is positive, like x squared, what direction are they going? Both end behaviors, what direction are they going? If the leading coefficient is positive, we are rising left and rising right, correct? So what if the leading coefficient is negative? What's happening to the left and the right? Think about if this said negative x squared. Yeah, because think of our transformation rules, right? That would cause a reflection over the x-axis, which means both directions are falling. Falling right and falling left. Does that make sense? So what if n is odd? Knowing the notes that we just took over here, make some assumptions about this category. And behaviors are opposite. Thinking about x cubed, like this, what happens if the leading coefficient is positive? What's happening to the left? What's happening to the right? Well, isn't this leading coefficient positive right here? Then tell me what's happening to the left and what's happening to the right. So falling left and rising right. Does that make sense? What about if the leading coefficient is negative? Again, thinking about transformation rules, that means this is reflected over the x-axis, so it goes like this, right? So, if the leading coefficient is negative, what's happening to the end behaviors? So, rising left and falling right. Does that make sense? Do you have any questions about that? Any questions about end behavior at all? Okay. Using factoring to find zeros of polynomial functions. Well, we talked quite a bit about factoring. In Algebra 2, we spent 4 or 5 days on it, right? Because it was hard? Or because there's a lot of different ways to factor? A lot of different ways, right? So let's look at this one. If we're going to solve this one by factoring, because if we solve it, aren't we finding the factors and the zeros? We are, aren't we? Okay. So just as a reminder, this is a trinomial. There's no greatest common factor. If there was, we would take that out first, right? So let's do AC. What's AC for this problem? Negative 30. What's B for this problem? So what two numbers multiply to be negative 30 and add to be negative 13? 3 and 10 are the first two I thought of too, but they would have to be opposite signs to multiply to be negative 30, right? And if they're opposite signs, I can't make 10 and 3 add to be negative 13, can I? Does that make sense? So what do you want to use instead? Negative 15 and 2. Okay, if I use negative 15 and 2, do you remember what I do now? Remember, I split the middle term. I rewrite this problem, split the middle term into the two parts that I just figured out. 6x squared minus 15x plus 2x minus 5. Okay? Now I factor by grouping. I look at these two terms and I say what's common in those two terms? 3x. What's left if I divide each of these two terms by 3x? What's left here if I divide it by 3x? 2x, good. What's left if I divide this by 3x? Minus 5, right? Now what's common in between these two terms? Right? You know I have to take something out, right? And the only thing they're both divisible by is 1, so factor out a 1. So I just have 2x minus 5 because anything divided by 1 is just itself, correct? Now what do these two terms have in common? A 2x minus 5. And if I factor out a 2x minus 5, what's left? 3x plus 1. Now here's the deal. If I multiply two numbers together and the answer is 0, what has to be true about at least one of these two? It has to equal 0, right? So I don't know which one, so I think maybe they both are just to cover all my bases, right? So I say 2x minus 5 equals 0. And I also say 3x minus 1 equals 0. Okay? Now this is kind of where you have to pay attention to what the directions are asking you. Okay? Because if it says factor the polynomial, you're finished right here. Okay? But chances are if it said factor, it wouldn't have this equal 0 on it. Right? If it says solve for the zeros, we have to keep going like we are right here. Does that make sense? So this row right here are the factors. So let's go find the zeros. Okay? So I just want to add 5 to both sides here to get 2x equals 5. I want to divide both sides by 2 to get x equals 5 over 2. It's as far as I can go, right? So come over here to this side. Add 1, 3x equals 1. Dividing both sides by 3 gives me x equals 1/3. These right here are my zeros. Yes, sir. Oh, thank you for that catch. So that means we got to fix this, right? This should be minus both sides. That should be a -1, so that should be negative 1/3. Thank you for that. You know how negative signs and I get along, right? Yikes. How are you feeling about using factoring to find zeros of polynomials? I know that's only one example, but we did quite a bit of work on factoring, and if you are struggling with factoring, please come and see me during Bulldog period. Please. Got it? So let's look at identifying zeros and their multiplicities. Did you even know that was a word? Multiplicities. Okay. So Let's start with this one. If that's what that equation was, my factors, what would my zeros look like? We can do this in our head, can't we? If I set this equal to 0, what would it be? -1, and this would be -1, and this would be -5, right? So how many solutions are there really? -1 and -5, right? I don't need to repeat the zeros when I write it down as my answers. But how many times did -1 happen? It actually happened twice, right? So this factor, or excuse me, this 0 right here actually has a multiplicity of 2. You can know that also because there's 2 of the same factors right here, okay? Another thing I want you to realize is that if you graphed this, I don't want to do this wrong. Let me fix it real quick. What in the world is happening? So I'm just putting this into my graphing calculator real quick. X plus 1, X plus 1, and X plus 5. Okay, so it's crossing. I'm going to get a different color. I'm not going to draw this all pretty and stuff. I'm going to get it pretty close though, okay? That's pretty close, okay? What do you notice about the intersection at -5 compared to the intersection at -1? So it's passing through -5, right? And how many times is -5 an answer? Once. How many times, or what happens at -1? It's turning, right? It's changing direction right at -1. How many times was -1 a solution? Twice. So sometimes looking at the graph will help with multiplicities, but you just have to be careful with that because this doesn't automatically mean 1 and automatically mean 2. It just means there's a multiplicity here. You might have to figure it out. Okay? Sometimes that might mean some synthetic division. Sometimes that might mean looking at your graph and your table and seeing if that will help out. What about this? We'll write this a little bit different as if we were graphing it on purpose. Okay? X plus 4 squared times x minus 5 to the third. Okay? So can you tell me where the zeros are, first of all? Where are the zeros? So at x equals -4 and x equals 5, right? How many solutions should there be to this problem? You remember that rule, the fundamental theorem of algebra that says that the highest exponent should be the number of solutions? Probably, right? Well, if I had a 2 here and a 3 here, then my highest exponent would be x to the 5th, right? If I multiplied it all out, it would be x to the 5th. So I should have 5 solutions, but I have 2. So you know I have some multiplicities, right? What's this one? How many times does this happen? Oh, look, it tells you. Yeah, twice, right? How many times does this happen? Multiplicity of 3. Okay, does that help at all? Does that make sense? So identifying zeros and their multiplicities. Identifying the zeros is just solving those factors for the zeros. Okay, looking at the multiplicities is figuring out how many times. This is a multiplicity of 2. This is a multiplicity of 3. Okay. Next is the intermediate value theorem. I know you've been waiting all day to figure out the intermediate value theorem, haven't you? Yeah. You're also terrible liars. Okay. So here's the intermediate value theorem. So we're going to say f is a polynomial function. So if f of a and f of b have opposite signs, there is at least one value of c between a and b where f of c equals 0. Okay, what? If f of a and f of b have opposite signs, so the value of the function, let me draw you a little graph on this. I think it might help to see what I'm talking about. Okay, let's pretend it looks something like this. Okay, and we'll say right here is a, and right here is b. Okay, if this is a, the value of the function at a, that's f of a, isn't it? Do you see how f of a is positive? And see, if this is b, right down here would be f of b. Do you see how the value of f of b is negative? This is above the axis, this is below the axis. So do you see how they have opposite signs? If f of a and f of b have opposite signs, there's at least one value of c right here where f of c is 0. Does that make sense to you? So you might be given an a value and a b value in a function and said, is there something in between these two? Well, first of all, you have to plug in a and b to the function to find out if they even have opposite signs, right? If they're both positive, chances are there's not a c in between them that has, because see, if this was c right here, a is here, c is here, is there a value where f of z is 0 between these two values? No. So this intermediate value theorem only works when f of a and f of b have opposite signs to start with. Okay? Any questions about the intermediate value theorem? Okay, last two. We're going to work on these two together. Understand the relationship between the degree and the turning points, and graphing polynomial functions. Okay? Graphing polynomial functions, on the face of it, is pretty simple because you just literally turn your calculator on and hit graph, right? But we want to be a little bit more intelligent about graphing polynomial functions than just using our calculators. We want to know what's going on beforehand. Okay? So if I ask you to graph this function, x to the 5th plus 6x to the 3rd plus 8x plus 1, I need you, before you even hit anything on the calculator, to be able to tell me the degree and the turning points. How many times does the graph change direction? Okay? So first of all, on this particular problem, can you tell me what the degree is? 5, because the degree is the highest exponent, right? Do you remember from Algebra 2, if your degree is 5, how many times it turns? 1 less. Okay? At least 1 less. It might be more. If it's more, it's either 4 or 2 or 0. It's never 3. It's 1 less and then 2 below that. Does that make sense? Okay, but we're going to say 5 and 3. Now, if I ask you to graph this, again, you could just hit the calculator and put this in to graph it, right? But we know just by looking at the equation, that if the degree is 5, it has at most 4 turning points. Okay, let me show you something real quick. After I turn it on. Whoa. Whoa. Clear. Clear. I ask you to clear, please. Clear. What is happening? Tab. Okay. So x raised to the 5th plus 6x raised to the 3rd plus 8x plus 1. So what's the problem here? Do you see 5 turning points? So did I do something wrong? No, the window is just not the right shape, right? It's not the size to be able to see all the turning points. So I could go ahead and change the window so you could see stuff, or I could just let you get started on your homework. Is that okay instead? I mean, I can try to adjust it so you can see it. It may just take a minute for me to figure out where all the turning points are so you could see them. You'd rather work on your homework? Okay. Do you understand, however, how to find degree and turning points? Yeah, degree is 5, turning points is 4. What if the degree was 7? Turning points is 6. What if the degree is 3? Turning points is 2, right? Okay. What if the degree is 2? One more thing. Do you understand what I mean by turning points? This degree is 2. How many turning points does it have? 1. It's decreasing, 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 increasing, increasing, increasing. Right? This degree is 3. So how many turning points should it have? 2. Does it have 2 turning points? Changes there, changes there. See? It might look a little bit more like this. A little more obviously turning there and there. But you understand what I mean, right? Okay. Do you have any questions about this? Any questions about any of these objectives we worked on today?